Hey, what's up? It's your old pal, Mr. Cook, and we are going to do a couple problems that I think are kind of fun from the extra practice of Unit 5 on probability. So I picked a couple of them that I thought were pretty interesting. We can get it done in a couple minutes. So this is like a quick short video of a few extra practice problems. Let's start off with number 6 here. So number 6, at a Boy Scout jamboree, there are 12 senior patrol leaders, 10 assistant senior patrol leaders, 21 patrol leaders, and 84 other scouts. How many committees of 2 senior patrol leaders, 1 assistant patrol leader, 3 patrol leaders, and 4 regular scouts can be formed? Well, it says one of the magic words, committee or group. You know, that implies it's a combination because it doesn't matter which 2 senior patrol leaders they pick, like Bill and Sammy, or Sammy and Bill. It's the same group, so that implies that it's going to be a combination because the order doesn't matter. It's just a group of people collected together. So I have 1, 2, 3, 4 different groups that I'm putting together. So since I have that many groups, to get the total group, I multiply each of these individual little groups together. So if I have a committee of 2 senior patrol leaders, I've got 12 senior patrol leaders, so that'd be 12 of them. And I'm going to do a combination of 2 of them, so 12C2. Then I have 1 assistant patrol leader, and I have 10 assistant senior patrol leaders that I have to pick from, so that's 10, and then choose 1. And then I have 21 patrol leaders, of which I'm going to pick out 3, so 21, and then a group of 3 of them. And then I've got 84 scouts, of which I'm going to get a group of 4 of them, so choose 4. So then it's just calculator time, type it in, and you get your answer, you know, whatever it is. 12C2 times 10C1 times 21 C3 times 84 C4. And you get a big old number. So it's 1 and then 6, 9, 3, 7, 1, 5, 9, 7, 8. Let me see, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So an additional 3 zeros after that. So it's roughly about 1, 6, 9, 3, 7, 1, 5, 9, 7, 8, 0, 0, 0 groups. Wow, that's a lot of committees. But yeah, you know, I mean, the number's humongous, but this is how you do the problem. Then, you know, just write down your answer. Okay, 7. 2 cards are randomly selected from a standard deck of playing cards. Let's assume that this is, because it isn't added in here, let's just say that it's without replacement. You know, like you pick out 1 card, and you just, you know, and then you pick out a second card. So find the probability that 1 card is an ace. So let's say it's the first card, and then the second card is a 10. So if you pick out the first card, there are 4 aces out of 52. And then for the second card, how many 10s are there? So there are 4 10s out of, now you took out one of the aces, so there's only 51 cards left. So then you just multiply those 2 fractions together and you get your quick probability. All right, you know, and then convert it into a fraction there. 4 out of 663. Okay. Neat. So that's another one. Let's do a couple more. 13. 2 6-sided dice are tossed. What's the probability that the total is 10? So how many different ways can we get 10 from 2 dice? Well, we can get, let's see here, 5 and 5, 6 and 4, 4 and 6, and that's it. 3 ways out of 36 different ways. So that reduces down to 1 over 12. There's our probability. Drawing from a standard deck of 52 playing cards, what's the probability that the card is a 10 or face card? So there are 4 10s, and the face cards, those are jacks, queens, or kings. There's 4 of each of those for a grand total of 12 face cards. There's no face cards that are 10s, so since there's no overlap, we just, you know, add them together. So that's a total of 16 cards that would be a success if we drew them out of the 52. And then that reduces down to 4 out of 13. So there's our probability for that one. A small business college has 800 seniors, 700 juniors, 900 sophomores, and 1,200 freshmen. If a student is randomly selected, what's the probability that the student is either a freshman or a senior? Well, there's no overlap between that. You can't, if you have a freshman, it's also a senior. So these are separate values. So we just add them together. 1,200 plus 800 is 2,000. That's the freshmen or seniors. And we divide that by the grand total, which is, let's see, that's 15 and then 27, so 3,600. I better add those up. I'm not trusting my adding skills right now. I don't know why. So 800 plus 700 plus 900 plus 1,200. Yeah, 3,600. Okay, cool. So then we reduce it down a little bit, and that's, let's see, 20 over 36, both divisible by 4, so 5/9 is what it reduces down to. All right, number 17. A magician is performing in front of an audience of 68 people. In order to do a demonstration, 6 people are randomly selected from the audience. So it doesn't say group or committee anywhere on here, but if it's just like, you know, the 6 people that they have, it doesn't matter if it's person A, person B, person C, person D, person E, and person F. That's 6 letters. Or if it was like, you know, person B, A, C, D, E, F. You know, like it's still the same group. So since it's still the same group, that's obviously a combination. So we have 68 people, and we're going to get a group of 6 of them. So we just type that into our calculator and get our answer for the different ways that we can put that group together. And it's 109453344. So 109,453,344 different groups. Wow, that's a lot. All right, let's do another one. Let's take a look at some more of these ones with the different notations. All right, so it tells us that A and B are independent events. So that means that if they're independent events, then the conditional probabilities are just equal to the event happening. So like the conditional part of it doesn't affect the overall probability, so just be equal to the probability of A. And then also the probability of B given A is just equal to the probability of B. So, you know, the overall probability doesn't change. It's distributed evenly amongst all the different other events. All right, so the intersection, you know, you'd have to like kind of solve one of these conditional probabilities, you know, to solve that. So here's what I'm talking about. Like if we know that they're independent events, then that means that the probability of the intersection it's true for the product rule. So the product rule, if you remember, is the probability of the intersection of these two events is equal to the probability of each individual event happening. So just multiplying them together. So, you know, to find this, I just need to multiply 0.4 times 0.3, in other words. That's why, like, knowing the definitions, like independent events or, you know, in a little bit, mutually exclusive events, is going to really help us out. All right, so anyways, independent events. So I multiply these two probabilities together to get the intersection. So 0.4 times 0.3, and I get 0.12. So that's my intersection probability. The union. All right, so the union, it doesn't say that these are disjoint events, so that means that I need to take the union as it is. So it's the probability of the two separate events added together minus the probability of their intersection. So, you know, just flat out type in the numbers. So 0.4 plus 0.3 minus the newly found intersection, and I get my total. Let's see what that is on my calculator. 0.4 plus 0.3 minus 0.12, and I get 0.58. So that's the probability of the union of the two events happening. So are the two events disjoint, mutually exclusive? Well, mutually exclusive means that they don't share any elements in common. In other words, the probability of the intersection of the two events for them to be mutually exclusive would have to be equal to 0. But as we see in the very first problem, we found out that the intersection is not equal to 0. So that means that no, they are not mutually exclusive. All right, last couple of problems. So find the probability of A given B. We already know that since it's independent, that means that it's just going to be equal to the probability of A, which is 0.4. The probability of B given A is just equal to the probability of B, which is 0.3. And then the probability of the complement of A, intersection of the complement of B. Ooh, that might be helpful to just draw a Venn diagram and see what this is talking about. So if I have event A in event B. So it's asking us to find the intersection between the opposite of A, so everything other than A. So I'll do vertical lines for everything that's not an A. So that's all this stuff. And then the opposite of B, so the complement of B, let me do horizontal lines for that. So everything outside of B would be all this stuff here. So it's asking us to find the intersection of that stuff. The intersection would be all the cross-section area, so it's like all this stuff. So that's kind of interesting, isn't it? Like what it's asking us to find is all the stuff that's not A. So in other words, it's asking us to find the probability of the complement of the union of the two events. And what that really means, with the complement is 1 minus the probability of the union. And we already found the union. The union is equal to 0.58, so 1 minus 0.58, which is equal to 0.42. So there's a little probability. This one would be a little bit too tricky for a test. We wouldn't probably ask that, but these ones are kind of fair game if you knew that it was independent events. All right, let's see which other ones did I map out. Mutually exclusive and that weird word problem. Okay, so let's see both of those because these ones go by pretty quick too. It says that C and D are mutually exclusive, and remember that mutually exclusive means that the intersection of the two events, or C and D, my bad. So the intersection of C and D is equal to 0. That's all it means. There's no common elements. So if I'm looking for the intersection of the two of them, I know that one, that's 0. The intersection of the union, since the intersection is 0, I just simply have to add the two events together to get the union. So it's going to be the probability of C plus the probability of D minus their intersection. And remember that their intersection is equal to 0. So this kind of goes away. And if I just add these two events together, I get 0.7. Find the probability of the complement, or I'm sorry, the conditional probability of C given D. Now, this is important to remember that the intersection is equal to 0. So the conditional probability is actually, if you use the formula, the conditional probability is equal to the probability of the intersection of the two events divided by the probability of the initial event happening. Well, shoot, because the intersection is 0, so the total is going to be equal to 0. So 0 for this probability. Same thing for this one, because the only thing I do here is put the probability of C in the bottom, but the intersection is still the same in the top, so it's also equal to 0. Now, the last couple, let's see, are C and D independent? Prove. Well, I'm just going to use the product rule here, and the product rule states that the probability of the intersection of the two events should be equal to the probability of each individual event multiplied together. But I know that that's equal to 0, right? And then each of these are 0.4 and 0.3. So does 0.4 times 0.3 equal 0? No, it equals 0.12. So they are not independent. They're dependent events. All right. And then, we already know what that's going to turn out to be. It's just going to be 1 minus the probability of the union of the two events. So we just did the groundwork for that. So there's the union, it's 0.7, so it's 1 minus 0.7, which is equal to 0.3. Easy peasy. One more. So I like this word problem. I thought it was pretty neat. A local band wants to get more fans. All right. So aside from that typo, it's a pretty cool problem. So they hand out, what the heck? They want to hand out 40 shirts with their logo on it to the first 40 people that go to their concert. If they have 10 smalls, 20 mediums, 15 larges, how many different ways can they hand out shirts? Well, one way that they can hand out the shirts is by handing out smalls to the first 10 people, and then mediums to the next 20 people. And then larges to the next 15 people. All right, so there's 10 smalls, 20 mediums, 15 larges there. How many different ways can they hand out the shirts? Well, that's one way. What if I switched up the S's here? You know, change this small shirt and this small shirt. Does it make a difference? No, it doesn't. So what this is really doing is it's just rearranging all the same stuff kind of over and over again, but getting rid of all the repeat stuff. This is the same type of problem that we had in the group work with the calculator thing, right? Because the different arrangements that we had, some of them had repeats, and to make a completely unique arrangement, we had to divide out all the repeats. So the same thing's gonna go here. So how many total shirts are there? There's 40 of them, or 40 letters. And we want to divide out all the repeats. So there's 10 smalls, so that'd be 10 factorial. 20 mediums, so there's 20 factorial because there's 20 of those mediums. And then 15 larges, so divide by 15 factorial. Then you just, let your calculator do the rest there. 40 factorial. Okay, let's make it look nice. Fraction, there we go. 40 factorial over 10 factorial times 20 factorial times 15 factorial. Whoa, that's a big number. So there's 7, all right, so then that'd be 0, 6, 7, 3, 6, 9, 6, 5, 2, and then that's 1, 2, 3, 4, 5, 6, 7, 8, 9, so an additional 0. So it's roundabout 70,637,696,520 different ways to hand out the shirts. Whoa, that's a lot. And yeah, that's how you do that problem. Pretty neat, right? All right, so that's it for this video. That's it on the little extra practice for the problems that I wanted to do. The rest of them are kind of like, some of them are a little really easy. Some of them are really hard, but I wanted to get kind of more mid-level problems because those are closer to the ones that are on the test. Okay, that's it. Good luck on your test. If you need additional help, make sure to check in with your teacher before school or, whenever you can. All right, that's it. Thank you very much.